A few months ago, and I will give the link in the description, I published a square wave oscillator made with a TL071 chip. The good property of that chip is that it has a field effect input. So the input impedance of such a chip is extremely high. That means that we can use, in such a setup, small value capacitors and get a good output. And then I mean an undistorted output with no damping, because there is no damping on the pins where that chip receives its capacitive and resistive effects. Anyway, pen over somewhat. This is that first circuit. I will give the link in the text box about my first experiments. Only problem was that the output here is extremely high impedance. That means, for instance, that when you connect here, say, a device to which you want to couple that square wave in, the square wave gets distorted due to, say, resistance here at the output, resistance from the output to ground, or capacitive effects from the output to ground. But anyway, this is, by the way, for a breadboard circuit, a very good circuit with which you can do many experiments. The capacitor Cx here sets the frequency in combination with the 100K potentiometer here. And to prevent all kinds of strange phasing effects, you must use, or can use here, a 1 mega ohm resistor that goes to ground, bridge with a capacitor of 1500 picofarad. So 1N5. And in that case you have a very good breadboard circuit that you can develop much better, etc., etc. And here is the pin connections of the TL071 at the front. So when we look on it here, like I've done it here, from the top. So this was my first experiment, and of course I wanted to make it better in a certain way, and I've changed the circuit over and over again. Was busy with it for approximately 1 week or so, or even more. But anyway, this is more or less the second circuit, and I want to demonstrate it, and after that I will say leave this circuit as it is. It's a very well usable circuit. It works with some, say, flaws, but of course you cannot expect to make a very good, always working function generator with the help of only one chip and 2 transistors. Anyway, it doesn't matter, I think. So, pen over the circuit as it is. I've made a description, a schematic. Here is the frequency, the potentiometer that sets the frequency. Here is a sort kind of trimmer potentiometer that is responsible whether the oscillator will work in a certain frequency band. Somewhat critical, but anyway. Here is a switch where we can switch between 100 picofarad and 10 nanofarad to get to another frequency band. Here is a potentiometer that corrects the waveform. Perhaps I'm going to show it when I have enough time. I only have 15 minutes. Here another potentiometer that corrects the waveform very important. So here is the oscillator circuit. Here we send out the signal out of the TL071 chip to a 1 transistor circuit, and that 1 transistor circuit is able to change the waveform from a square wave to a triangle wave. So here the circuit again. I will slowly pan over, and perhaps interesting to tell that when we lift up the frequency, the waveform changes. And you can set the waveform here, the frequency band here, by changing between these two capacitors, 100 picofarad and 10 nanofarad. You can do also an experiment with 100 nanofarad. I'm not going to show that. Here the pin connections. So here we switch the frequency band, and you will surely see, and I will demonstrate that on a certain frequency the square wave changes into a not very proper square wave here, and finally on the highest frequency on a kind of triangle wave. And with a 100 picofarad capacitor, we go from 18 kilocycles with this waveform to 131 kilocycles. And well, that is of course uh, 15 August 2022. That is of course interesting that you can get to a so high frequency with 131 kilocycles with this simple setup. Pan over somewhat again and want to show the circuit in its completeness. So let's see what this circuit can bring. Switch on my scope. My scope is also my frequency counter. I will switch off all the lights to get a proper view. So what's the situation now? We are with this switch here on a certain frequency, and it is the highest frequency that the circuit can bring. And you can surely see that it is a triangle wave on 131 kilohertz. That's very high. Let's turn the potentiometer here, the frequency potentiometer, see what happens. Of course, so at the same time you see that the waveform changes and the frequency changes anyway. And very important, of course, also this is a very simple setup. The amplitude changes. So now we are on 18 kilohertz with this waveform, and as far as I can see, the 10 nanofarad capacitor that sets the frequency in combination here with this potentiometer. Let me try to show the effect of the waveform corrections with the help of these two potentiometers. So here you can see that by turning this potentiometer here, the 1K potentiometer here in the circuit, this 1K potentiometer here, changes the waveform and to a good, say, square wave on 18 kilocycles. And I have to put the camera down for a while. I hope that doesn't drop. You can also change the here with the 50K potentiometer. I will show it the duty cycle, and also that refers also directly to the frequency. You can also see that on the higher frequencies the square wave gets somewhat other angles, but anyway, I think it's useful. It's a useful circuit. That's what I wanted to tell. Well, 18 kilocycles, and here the other potentiometer can also correct the waveform somewhat. That is the 25K potentiometer in the circuit. That's here, 25K. I'm turning it now here, and you can also see correction on the waveform, especially here a somewhat lesser overshoot. Anyway, I switch now to the other capacitor. Let's see what happens. Now we are on 10 nanofarad and we are on 241 Hertz. I turn the duty cycle and frequency potentiometer again. Let's see what happens. We are on 811 Hertz and at the same time a very good proper square wave. This is the effect of the turning of the duty cycle potentiometer. I now go to the frequency potentiometer. Let's see what happens. Of course the frequency gets higher and higher and higher, and we are here on 9.2 kilohertz approximately. Let me show the effects of the frequency, the waveform correction potentiometers. Here you can see that effect. You can surely see that the square wave gets another slope here. That has an effect. Of course, when you use such an oscillator as a driver for a transistor or whatever, that will surely have an effect. And now the other potentiometer, it gets more and more steep. So here are all the say control mechanisms to give the waveform the ideal form that you need. I cannot do the demonstration longer. I only have 15 minutes. Thanks for watching. So I only want to pan over somewhat. It's a properly working square wave, triangle wave oscillator. Can be made on a breadboard, can also be made in a semi-professional way. I have to say that pin connections here of the used semiconductors. I have to say that this output, I wanted to use here a field effect transistor as a output, say to make the output level regulated, but that was no success. So anyway, perhaps even this circuit, though it performs quite good, needs here a kind of elaboration. Anyway, I think it's an interesting circuit, useful circuit, so that's why I publish it. Thanks for watching. This capacitor here of 100 picofarad plays a role, and I have not drawn that in the circuit, so sorry for that. Between here the collector and the base there is a resistor. That resistor is 100K. No. Oh, here it is already 100K, so sorry for this, forget this, this is okay. This is okay, the circuit is okay. So here is this transistor gets its bias via the 27K resistor here and the 10K resistor here. And here we have the second transistor that gets its bias out of the 100K resistor here. And I wanted to tell that this 100 picofarad capacitor has an effect on the waveform. So, perhaps I have to do a kind of correction. Sorry that this video went this way, but the circuit, like I showed it, is okay, and I don't want to make the whole video all over. So no connection here either. This is how it is. Yes.